Welcome for part 2 of lesson 310. We're going to talk about trigonometric inequalities today, and so let's take a look at the first example. We've done inequalities with polynomials and rationals. We are also going to be using similar strategies for our trig functions. So example 1, we've got a graph of f right here. It's defined from negative 2 pi to 2 pi. So those are endpoints. What are all values of x for which f of x is less than or equal to 0? On the graph, this is pretty easy. Our y value, f of x, the vertical distance, has to be less than or equal to 0. We are equal to 0 right here. We are below or equal to 0 here, and then again here. So when I answer this one, I'm going to go ahead and say f of x is less than or equal to 0 when x is equal to negative 2 pi. That's just that one point. We'll also include negative pi is less than or equal to x is less than or equal to 0, and pi is less than or equal to x is less than or equal to 2 pi. All right, that's pretty straightforward. Now, obviously, we're not always going to be given a graph, so it may not always be quite that simple. The second example is going to obviously get more complicated. What are all values of theta from 0 to 2 pi, so our domain's limited, for which sine of theta is greater than or equal to root 2 over 2? So this is more complicated. It's not just comparing it to 0. Some things I want to notice is that we're talking about sine values. So in this case, sine values are y values. So that's something that we want to make sure we remember. Since sine is the vertical displacement, we are looking for times when the vertical distance is more than root 2 over 2. So if I look at this, when is y equal to root 2 over 2? I notice it happens right here, and it also happens over here. So those are y values that are equal to root 2 over 2, which means that you also have any time that it is higher in the vertical direction. So that whole arc right there is equal to or greater than root 2 over 2. So what are these values? That's pi over 4, and this one here is 3 pi over 4. So you can just say when pi over 4 is less than or equal to, we used x is less than or equal to 3 pi over 4. In this case, there's your answer. Pretty straightforward, but a lot of times they won't give you this unit circle, so you're going to need to be able to figure out these values without that unit circle. So that's why in class we're going to do some unit circle practice. Next example, 3. Now we're going to have to do this one algebraically because there's some math that needs to be done in order to isolate our trig function. F of x is equal to this equation, g of x is equal to 3, and we want to find all values of x in the xy plane from, our domain is restricted to 1 period, when f of x is less than g of x. So I'm going to put 4 plus 2 cosine of x is less than 3. Let's isolate our trig function using inverse operations. Less than 3. We love this problem. We have 2 cosine of x has to be less than negative 1, so cosine of x has to be less than negative 1/2. Hopefully you follow me to this point. Now that I have my cosine isolated, I can figure out the actual values here. When is cosine less than negative 1/2? Let's think about our unit circle. cosine, remember, is the x value on our unit circle. We have -1/2 for the x value. Starting here, this would be 1/2, so that's not going to work. I'd have to jump over here to -1/2. Right here, -1/2 √3/2 happens at, that angle would be, what would that angle be? 2π/3? Yeah, 2/3 pi. And then that means, since we're looking for values less, and we're talking about x values, I'm going to be looking for values that are further to the left, which will go all the way around this unit circle until I hit this point right here, which is -1/2 √3/2. So anything in between these values right here will give me an x value less than -1/2. So in this case, those answers are 2π/3 is less than or equal, because it can be equal, to x is less than or equal to 4. This would be 4π/3, or 4π/3. All right, so make sure you've got a unit circle, or, follow along by thinking through it using the hand kind of trick. Example 4. This one here gives us h of x and k of x. We have our domain restricted to 1 rotation on the unit circle. We want the h3 cosine of x to be greater than √3 cosine of x. In this case, that's plus. I want to get the cosines all together, so I'll subtract 1. That gives me 2 cosine of x is greater than √3. Guess what I'm going to do? Yep, divide. So cosine of x has to be greater than √3/2. So now, unit circle, cosine, we want x values that are greater than √3/2. X values means we're going to focus on horizontal distances. So √3/2, let's see, that would be an x value right here. √3/2, 1/2. That is at π/6 radians. To be greater than that, we need to be further to the right. So then that would also reflect down here to this. That would be 11 π/6 radians. And so our solutions would be on that arc right there. The weird thing about this is, because of the domain, in my head I thought, from 11 π/6 to π/6, but that doesn't make sense. When we think about, the way that we use our notation, we want to go least to greatest. So this technically, while it looks like 1 area, we write it as 2. Because we're going from 0 is less than or equal to x is less than or equal to π/6. And we have our second one, I guess not and, but or, because either would work, or 11 π/6 is less than or equal to x is less than or equal to 2 pi. So we have to think of this as 2 separate ones, because we have the start of the unit circle and the end of the unit circle. So that's a little bit weird, less intuitive than the others. Cool. Now, going down here, we're going to solve some trigonometric inequalities. We've got some steps here that I would like you to read through on your own, and then I'm going to apply them, because now we're going to start mixing in some more quadratic types of problems. So, first thing we want to do is take this and set it equal to 0, essentially. We'll come back to the less than sign in a little bit. and I want to solve 2 sine squared of theta plus sine squared, plus sine of theta is equal to 0. Solving for theta here, you can treat this just like you would treat 2x squared plus x equals 0. You're going to use the same algebraic manipulations that we would use for that. So here we go. I'm going to divide out a sine of theta, and then that leaves me with 2 sine of theta plus 1 is equal to 0. Then I'll solve sine of theta equals 0. And sine of theta, our y value, gives us a 0 at either 0 or pi. But we also want to remember that 0 can be included and pi can be included. But also 2 pi, which would be a return to 0, is also included in this domain. So I need to include that as well for this first one. Now, the second factor was 2 sine theta plus 1 equals 0. I solve this and find that sine of theta is equal to negative 1/2. When is sine of theta equal to a negative 1/2? You can get out your unit circle that we've been using. You can memorize it, hopefully, but those answers are theta is equal to 7 pi over 6 and 11 pi over 6. Now, from there, we have a bunch of solutions, but remember, inequalities, we want to find out when we are above the axis, or actually in this case, below the axis, because we want to be less than 0. To do this, I will create a sign chart. When will sine of theta and 2 sine theta plus 1 be greater than or less than 0? Well, the solutions are at 0, pi, 7 pi over 6, 11 pi over 6, and 2 pi. So I'm going to now create a sign chart to find out whether or not this whole function will be positive or negative on these intervals. All right, I got my fancier unit circle that's easier to read because I think it'll make this part a little clearer. First off, we know that this has a domain restriction, so I don't need any values below 0 or above 2 pi. Now, let's start with the simple one, sine of theta. When sine is between 0 and pi, 0 and pi being 180 degrees, all of those sine values, which are the y values, they're all positive. Between pi and 7 pi over 6, which is right here, those y values become negative numbers. And from 7 pi over 6 to 11 pi over 6, the y values are still negative because they're still below 0 all the way until we hit 2 pi or 0 degrees again. So that one there is going to be positive for the first 2 quadrants and then negative for the rest of the unit circle. The second one is a little more complex, and so I want to bring it back to this equation, or this factor, really. We said that this factor, we want them to ultimately be less than 0, right? We used an equal sign just to make it simple to solve, but if we think of it back here as an inequality, that means we want that sine of theta to be less than negative 1/2. Why is that? Well, let's see. If I look at my unit circle and the output is negative 1/2, that would be at 7 pi over 6. That's where a sign is going to change, because watch what happens. If we plug in 2 sine of 7 pi over 6, the angle there, plus 1 is less than 0. Well, at this point, sine of 7 pi over 6 we said is negative 1/2. 2 times that means you have negative 1 plus 1, so 0 is less than 0. This is the point at which this function switches, right? It goes from being above that. So even though in here it seems as though the signs have become negative, because of the numbers we're plugging in being manipulated by this 2 plus 1, these numbers keep it positive up until we hit this value. So if I go back to this function right here, we are positive for sine values here still. But then after we get past pi, this function, because of the equation around it, is still going to remain positive from here to here, 7 pi over 6, because these values will be accounted for by the plus 1. So it's still positive right here. Now, after this point, these values become larger than the 1, and so they become negative up until we get over here where we have this negative 1/2 happening again. After this negative 1/2, these numbers are now going to be small enough in this area, so here and here, they're small enough in that area to be accounted for by the 1/2 that we are going to get out of solving. So it becomes positive again right here. To make that clear, normally we would look at the sine values and just determine if they're positive or negative. However, given that we have a manipulation of multiplied by 2 and adding 1, when I solve, I get negative 1/2. The negative 1/2 for sine is now the switch between positive and negative. So this is where we trade positive and negative values. Overall, this function then is positive from 0 to pi, negative from pi to 7 pi over 6, positive here, and negative here. What do we want from this function? Well, we want it to be less than 0, so that would be from pi is less than or equal to x is less than or equal to 7 pi over 6, or 11 pi over 6 is less than x, less than or equal to 2 pi. Psych. Look at the original signs. Not equal. It should just be less than. So don't put the equal part on there. That was my bad. Here we go. We've got a values of theta from 0 to 2 pi where this function is greater than 0. If you look at this function, it's set up just like a quadratic. You may even want to think of it as though it is a quadratic like this, where to find when it's greater, you would factor it. So when you factor this quadratic, you'd have 2x times an x, and then to get a negative 1, you'd have a 1 and a 1. One of these has to be negative. Since the middle term is positive, I would make the multiplier with 2 positive, and this one would be the negative. So then here, I just take that, and instead of x, it's a cosine theta. So it's the same exact strategy for factoring, except that I have the cosines involved. Now that I've got that, I'm going to take each of these and start by just setting it equal to 0. When I solve this, add a 1, then divide by 2, and I'll have cosine of theta equal to 1/2. Cosine of theta is equal to 1/2. If you look at your unit circles, you'll find that those values happen at pi over 3 and 5 pi over 3 because I'm looking at the x values. So pi over 3 right here, 5 pi over 3 right down here. The next one is cosine of theta is greater than -1, because I'll subtract the 1. We can treat this as though it's equal for now, just to answer it. So that means that theta would have to be equal to pi. That's the only time cosine is -1. And now I'm going to set up my sine chart. Remember that we go from 0 to 2 pi on this sine chart because those are the values that I'm limited to in the domain. The first value that we found that was a solution is pi over 3, then pi, then 5 pi over 3. So at each of these, we'll see some sort of maybe sign change for the factors. Now, to make sense of this, whatever the value is that I plug in here has to be greater than or equal to -1. So, if that's true, then the sine chart will read positive. So cosine of theta is greater than -1. Well, literally, every cosine is greater than -1 until you get to pi, where it's -1. But even if it's -1, that is still equal to -1. So for this first one, I'll put cosine is greater than 1, -1. That's true for literally every single one of these domains or range or values. Now, the second equation, the 2 cosine of theta turned into cosine of theta had to be greater than 1/2. If cosine of theta gives you a value greater than 1/2, you put a positive because it's going to be greater than 0 when you plug it in. So let's go ahead and think about cosine values, x values that are greater than 1/2. In this case, starting at 0, we're at 1 for cosine. That is greater than 1/2. This is greater than 1/2, greater than 1/2. Oh, here's where it's equal to 1/2. So from 0 to pi over 3, we're greater than 1/2, which is what the inequality said, so that'll be a positive. After pi over 3, the x values are now less than 1/2. They're going down to 0, then down to negative numbers. So the x values are all negative all the way around here until I reach that 1/2 again, because all of these are going to be less than 1/2 for your x values, right? All of these are less than 1/2 for your x values. So this will be negative because it's less than the half. This will also be negative because it's less than the half until we hit 5 pi over 3. Then the x values become more than 1/2. So it'll be positive when you plug in to the actual equation. Now from there, we wanted this overall function to be greater than or equal to 0. So greater than, we're looking for positive values, will be from 0 is less than or equal to x is less than or equal to pi over 3. And, 5 pi over 3 is less than or equal to x is less than or equal to 2 pi. Because those values multiply together to give us positive solutions. There we go. This is a lot. Come in ready to practice, but please be ready to ask questions. These are tricky.